Welcome to the Explainer. Today, we're going to pull back the curtain on the strange and, honestly, powerful principles that govern the hidden world of light.
Okay, let's dive right into this with the most fundamental question about light. A question that, it baffled scientists for centuries. Is it this continuous wave, like a ripple in a pond, or is it more like a stream of tiny little bullets of energy?
Well, the amazing answer is, it's both. Yeah, it's kind of weird. Some of light's behaviors, things like interference and diffraction, they only make sense if you treat it as a wave. But then other things, like the photoelectric effect, only work if you see light as a stream of particles we call photons.
So here's the crucial point. Mastering this split personality isn't just some weird physics problem. No, it's the key that unlocks absolutely mind-blowing technology, a lot of which you and I use every single day.
Okay, so let's start with the first rule of light's wave-like behavior, something called interference.
Just imagine ripples in a pond for a second. Where two of the crests meet, the wave gets bigger, right? That's what we call constructive interference. But what happens where a crest meets a trough? Well, the water goes flat. That is destructive interference. And believe it or not, light waves do the exact same thing.
And this principle has some incredibly clever applications. You see it every day in the anti-reflection coatings on your glasses. There's this super thin film on the lens that creates a reflected wave that is perfectly out of sync with the light bouncing off the lens itself, and boom, it cancels it out for clear vision. It's the same basic idea behind advanced tools like OCT that can map the structures inside your eye.
All right, let's move to our next rule and see how this all builds up. Let's talk about diffraction, which is what happens when a wave bumps into an obstacle.
You'd probably expect light to cast a perfectly sharp shadow, but it doesn't. Instead of traveling in a perfectly straight line, light waves actually bend and spread out just a tiny bit as they pass a corner.
And this beautifully illustrates a real-world trade-off that happens in our own eyes. So when it's bright out, your pupil gets small, which increases your depth of field. It makes more things appear in focus. But if your pupil gets smaller than about 2.5 millimeters, diffraction actually becomes the problem, creating a blur that sets a hard, physical limit on how sharp your vision can possibly be.
Our final rule for understanding this whole wave world is polarization, and this one is all about controlling the direction of light's vibration.
Think of it like this. If you're shaking a rope up and down, side to side, all over the place, and then you try to pass it through the slats of a picket fence, what happens? Right, only the up and down vibrations are getting through. The side to side ones get blocked. That's polarization in a nutshell.
This is exactly why polarized sunglasses are so amazing at cutting glare. That really annoying glare you get from a flat surface like a road or a lake, it's mostly made of light waves vibrating horizontally. The lenses in the sunglasses act just like a vertical picket fence, and they block that horizontal glare right out.
So, okay, we've learned the rules of interference, diffraction, and polarization. So now what? What's the big payoff? What happens when we use all this knowledge to command light with incredible precision?
We get lasers. And lasers have become one of the most powerful and precise tools in all of modern medicine, letting surgeons interact with human tissue in three very distinct and frankly amazing ways. First up is photocoagulation, where the laser basically acts like a microscopic cook. The light gets absorbed and converted into heat, and that precisely cooks tissue to seal off leaky blood vessels, often in the retina. Then you've got photoablation. This is the master carver. This one uses high-energy UV photons to break molecular bonds directly, just vaporizing tissue with pinpoint accuracy. That's the magic behind corrective eye surgery. And finally, there's photodisruption, which is like a tiny, focused hammer. An intense, super short pulse creates this miniature shockwave that mechanically tears tissue, which is how surgeons can clear up membranes that sometimes cloud up after cataract surgery.
So from a simple question about waves and particles, we've literally unlocked the power to perform surgery without a scalpel. It really makes you stop and wonder, now that we've mastered light, what invisible force are we going to command next?